Hello everyone. Today I'm going to cover how to perform impact tests on turbo machineries. From small to large turbo machines, it is important to perform impact tests on the rotor. Because as the rotor spins, they are the main source of vibration. So it is important to understand the dynamic characteristics of the rotor, which ties into the overall machine vibration. Eventually, the impact test helps to identify when the energy source amplifies to a large vibration. So understanding the energy source is important if you want to reduce the vibration, but your machine is operating in a high speed, such as turbochargers in automotive. In the early design stage, it is important to perform impact tests and compare the test result to the rotor dynamic model. Here is how the process flows. You first model the rotor assembly, as shown on the right side. Then you perform the rotor dynamic analysis, which you can predict the mode shapes of the rotor. From here, it is important to perform impact tests and compare the test result with the rotor dynamic model. The red dots are the prediction from the rotor dynamic analysis. The blue dots are the measurements from the impact test. It is important to make sure that the prediction represents well the measured value. If there is a large discrepancy between the impact test measurements and the rotor dynamic prediction, you need to adjust your rotor dynamic model. Eventually, the end goal is to predict the critical speed so that you design your machine better to overcome any vibration issues. Alright, here I'll give you a more detailed example of how to perform an impact test for a simple rotor shown in this slide. The used instruments are listed on the right. The schematics of test setup is shown here. Two accelerometers are connected to the signal conditioner and then they are routed to the dynamic signal analyzer. Please note that to evaluate the mode shape of the rotor, you need at least two accelerometers to not only measure the natural frequency, but also to obtain the mode shape of the rotor from the impact test. First thing you need to do is to mark the rotor equally spaced. The total length of the rotor is about 25 inches. So let's mark every 1.5 inches equally spaced along its entire length. Now attach two accelerometers on the rotor. As the name indicates that the stationary accelerometer will stay at its location, while the roaming accelerometer will move around during the impact test. Once all the equipment is ready, impact on the rotor so that two accelerometers get the signal. Impact. Once the signal is recorded in the data acquisition, record the AR, AS, and the phase angle between the accelerometers at each natural frequency. Once you record all the data in your Excel sheet, move your roaming accelerometer to the next interval location and then repeat the impact test. Impact. Then record data. So the process looks like this. Move the roaming accelerometer to the next location, impact the rotor, record the data. Move the roaming accelerometer to the next location. Then repeat this process until you measure all the data through the whole rotor. But if you have many accelerometers in hand, you could perform impact tests with reduced number of movement of the accelerometers as shown in this figure. But the weight of the accelerometer can affect the natural frequency of the part you are measuring. So if you are testing a light-weighted small shaft, it is better to test with small number of accelerometers that are also light-weighted. Alright, let's look into the collected data from the impact test. If you have recorded the data at each natural frequency, the data would look like this. This data set is for the first natural frequency of 196 Hz, with data recorded at each interval. Now, if you multiply all the recorded data, you will get the mode shape amplitude. If you plot this amplitude versus the intervals, you will get the mode shape for the first natural frequency at 196 Hz. Same logic applies for second natural frequency at 396 Hz. If you plot this amplitude versus the interval, you will get the mode shape for the second natural frequency at 396 Hz. Now, let's compare the impact test result to the rotor dynamic model. To do so, you need to model the rotor geometry into the finite element tool as shown below, and then run the analysis. Here are the natural frequency and the mode shape result from the impact test, and prediction from the rotor dynamic model. Both natural frequencies and mode shapes are very similar to each other, which indicates that the rotor dynamic model represents well the reality. This means that we could use the rotor dynamic model to predict the rotor responses with high confidence. In other words, the predicted results have a high chance of representing what will happen in real machine. So let's talk more about how your model applies to predicting the rotor dynamic responses. I'll give you an example here. Say this rotor is installed in a test bench, with elliptical journal bearings installed at each end. If you know the detailed geometry of the bearing, you could predict the stiffness and damping characteristics of the bearing using the commercial software. Here is the predicted bearing stiffness and damping versus the rotor speed. Then you feed the bearing stiffness and damping information back into your rotor dynamic model. Now you could predict the critical speed and the threshold speed of instability. Then you run coast up and coast down experiments and experimentally obtain where the critical speed is and when the instability occurs at what speed. If your rotor dynamic model is well modeled, it gives ample information and can give you early warning related to when the failure could occur. And the impact test helps you to increase the confidence of your model. Alright, this is all I have for you today. If you like this video, please subscribe my channel. Thanks for watching, and I'll see you in my next video.